It's kind of a fun one, exponential decay. We start with the penny lab where we have 100 pennies. And basically what I do is I ask the class if I flip these pennies or just basically dumped them on the desk and pulled out all the tails and just went with the ones that were heads, how many rounds would it take me to have no pennies left? So again, how long would it take me to go through 100? And sometimes, the guesses are kind of comical, but if you think about it, what really should happen would be this. And it wouldn't be exactly this, but it would be roughly this. That I started with 100, and then, half of them should be heads and half of them should be tails, and then that should happen again. And then here, I don't know, let's call it 12 instead of 13. The math gets a little bit easier. Obviously, half of 25 is 12 and a half, but I'll round down. So this time I'll round up. So instead of it being 1.5 and rounding to 1, I'll round up and call it 2. So at this point, you're looking at, I don't know, 0 or 1. You're looking at 7 or 8 rounds is roughly what it should take. And like I said, sometimes the guesses I get are a lot higher than 7 or 8 rounds. But I hope it makes sense as to roughly how many rounds you would expect to see all these pennies disappear in. It says, is it possible that a team conducting this experiment might never remove the last penny? Yeah, I mean, when we have 1 penny, it's a 50-50 chance, right? In theory, I could keep getting heads on that one and it would never go away. So with the results of this experiment being different if you'd remove the heads instead of the tails, well, in theory, it wouldn't have been, right? I mean, we would have the same numbers here, we would think. It just, you're just likely to get a tail as a head, so it wouldn't matter. And what if you started with 200 pennies? How long would it take? Would it take 14 or 15 rounds? Well, no. It would actually just take 1 extra round, right? So that first round would eliminate half of those. So kind of interesting, not always what people seem to think. So even with 200 pennies, you're probably looking at 8 or 9 rounds instead of 7 or 8 rounds. Again, not a rule though. You could get more or less. So decide what your independent and dependent and independent variables are for the penny lab. Well, I think this would be the number of rounds. So that would be my independent variable or my x variable. And I think the number of pennies or y would be my independent variable. So I think it asked me to do this later, but I'm going to go with round 0 has 100 pennies, right? I haven't begun the investigation. Then it goes 25, and then it goes, 50, then 25, and then 12 and a half, and then 6, and then 3, and then 1, and we get this asymptote where in theory we never quite hit 0, but in reality you're probably going to hit 0 at some point. So the question would be, and we're going to get to this in the next lab, but in the next question, but I want you to see this now. Some of the questions they're going to ask are, should this be continuous or discrete? Well, is there a round and a half? I don't think there is. Or is there like 2/3 of a penny? I don't think there is. So I think this should be discrete. I don't think we want to connect these dots and make them continuous. The other thing is we have an asymptote right here technically. In reality, because we have to round that penny, right? You're not going to have 0.2 of a penny and 0.1 of a penny, etc. We probably would hit the x-axis at 0. But technically speaking, if we were just cutting those pennies in half over and over and over again, we would have an asymptote and we would never really reach 0. So I hope that makes sense. Again, kind of keep this graph in mind as we jump along here. Take 814 part B. And again, we had already kind of graphed that, and we're discussing some of these questions. So we have the transparencies. You would have done these on transparencies. We would have looked at them. So is it increasing or decreasing? It's obviously decreasing. It's going down. What does this mean about the multiplier? Well, the multiplier must be between 0 and 1, right? It's got to be less than a 1 multiplier if it's getting smaller. And again, we don't deal with 0 and negative in this book. So we can be confident between 0 and 1. Using what you know about the probability of flipping a fair coin, what would you expect the estimate for the multiplier to be? Well, I would expect it to be a half, right? Half times heads, half times tails. So write the equation of the exponential function. So I would say y equals 100 times 1/2 to the x. I think that's what I'm looking at there. What does the function give you x equals 0? Well, we already said that. It gives you 100, right? And that's how many points you started, how many coins you started with. Could there be an x equals -1? Yeah. It might mean that we had a round before we actually started, like a practice round or something. I don't know. We started with 200 pennies at x equals -1, and then at 0, 100, we started keeping track or something along those lines. The point is, it is possible. In the context of this situation, what should the domain of the model that you wrote in part C be? Well, I would say the domain should be 0, 1, 2, ... Again, we could have a negative, but in terms of this actual problem, I would say we started with we started with round 0 and then worked our way up. So although a negative is technically possible, I don't think it describes the situation very well. But again, what I think is really important is that we understand there's no decimals, there's no part 0.2 rounds or anything like that. Does the graph in part F look like any graphs you've seen? Yeah, we've seen some exponential decline. And again, what we're basically saying is it just looks something like this. And we've definitely seen some problems. There was like some rabbit population problems and stuff like that that showed some exponential decline previously. All right, let's go ahead and jump to problem 856. Uh-oh. All right, so 856. Half-life. Carbon-14 dating is used to approximate the age of ancient discoveries and to learn more about things like dinosaur fossils. Scientists have studied the rate of decay of carbon-14 and have learned that no matter how much of this element they start with, only half of it will remain after 5,730 years, which is called the half-life. So if you have 20 grams, you're going to have 10 grams in 5,730 years. If you have 1,000 grams, you're going to have 500 grams. So no matter how much you start with, it cuts in half every 5,730 years. So all living things on this planet contain the same proportion of this carbon-14 relative to the amount of overall carbon in their bodies. Knowing how much carbon-14 to expect, scientists can then measure how much carbon-14 is left in ancient items to figure out how much time has passed since the object was living. So if a living object is supposed to contain 100 grams of carbon-14, how much would we expect to remain after one half-life? Well, we'd expect 50 grams because it would be cut in half. How about 2? Well, this 50 would be cut in half, so we'd expect 25 grams. Draw a graph showing the expected amount after X lives. Well, again, if we had 100 grams, we would expect that after 1 it would go to 50, after 2 it would go to 25, after 3 it would go to 12.5, after 4 it would go to 6. So it would look exactly like the one that we just did with the pennies up here. I guess on the other sheet. Sorry, it's gone now. So write an equation for the half-life. So we would say y equals, we started with 100 to the x. So it's the exact same equation that we had when we were doing the penny lab. We started with 100. So in addition to help you learn about exponential decay, half-life also provide insight into in the meaning of exponents that are negative or 0. So this is going to be some negative exponent stuff you guys might remember from chapter 1. So using your function from the previous problem, what output does the function x equals 0 have? Well, anything to the 0 power equals 1. So a half to the 0 power is 1. 100 times 1 is 100. So does this make sense? Yeah, it does make sense. We started with 100 grams. So when time was 0, there was 100 grams. So according to your graph, how much carbon-14 should there be when x equals -1? Well, again, let's do a table real quick and see what's going on here. So it seems to me that if I go back to -1, this should be 200, right? I mean, that makes sense. And that should make a lot of sense because when you have a negative exponent, what happens is they jump across the fraction and turn positive, right? That becomes, actually, you know what I should do? I think I kind of skipped a step for convenience sake. I can distribute that exponent in. So it really looks like this, which is the same as a negative exponent jumps across the fraction and turns positive. So I get 2. Well, that makes a lot of sense that 100 times 2 is 200. So now calculate the output for when x is negative 2. Well, when x is negative 2, it looks like it should be 400. But again, we can use what we have here, 1/2 to the negative 2 power. Well, that's going to be 1 to the negative 2 over 2 to the negative 2, which is going to equal 2 squared over 1 squared, which is going to be 4 over 1, which is 4. And that makes sense. 100 times 4 is 400. So we can see that works out quite nicely. So what about when we have these ones right here, right? 3 to the negative 2nd power. Well, if I have 3 to the negative 2nd power, that's the same as 1 over 3 to the 2nd power, which is 1/9. And what about if I have 2/3 to the negative 2nd power? Well, like we discussed, that should be 2 to the negative 2nd over 3 to the negative 2nd, which would be 3 squared over 2 squared. They just move across the fraction and turn positive. So I get 9 over 4. So those are going to be some different solutions there. And then finally, using what you came up with here, let's go ahead and solve these. Well, this would obviously be 5 to the 1st power. This one would obviously be 8 over 5. Again, you can put them to the 1st power. It's not really important. The 1st power doesn't change anything. This is going to be 3 to the 2nd power over 1 to the 2nd power, which would just be 9. This one is going to be 3 to the 3rd over 2 to the 3rd, which is going to be 27 over 8. 3, 9, 27, 2, 4, 8. This one would be b to the 1st over a to the 2nd. And this one might be worth kind of doing down here. This one might be a little bit confusing. So the first thing I would do is I would distribute that negative. So it's really a to the negative 2nd over b to the negative 1st. Now you can see those exponents move and become positive. So that's why I think skipping that step might have been a little confusing. And then finally, last one, I'll just go ahead and write over here. That way we don't run into the same problem. The first thing I'll do is I'll distribute that negative. So I'm going to get x to the negative 3 over y to the negative 6th and z to the negative 3rd. So these are going to kick up and turn positive, and this is going to kick down and turn positive. So this is what I'll get for this one. Y to the 6th over z to the 3rd, x to the 3rd. So I hope these equations that have declining values make sense, and I hope that this review of negative exponents makes sense. If not, always feel free to reach out and ask some questions. Have a good one.